Next, we're going to get into some of our corrosion-resistant particle technology. The particles are really what drive a lot of the corrosion resistance in a lot of these systems. So if you're looking at this table, what you see on the left, the metals, is known as the Galvanic series. You'll see them ordered actually in terms of how noble or how active they are, with the ones at the top being more noble or less reactive.
So Ben, why does it matter if materials are more noble or more active?
Typically, when it comes to galvanic corrosion, when you have two different metals, the material that's less noble, or in this case, lower down on the chart, ends up being the one that's corroded or eaten away or dissolved fastest. So if you look here, you can see aluminum, which is a very common material in a lot of applications because of its cost, its weight, its workability, ends up being lower on the galvanic chart, which means it can actually take the most damage in a lot of systems. That's why you see the fillers on the opposite side, on the right side of the chart, used to make sure that you're getting the best possible interface and minimizing the difference in that potential.
And one thing I want to point out too is on the left, you see all the different materials, different metals in the chart. Most likely, you're not going to be able to get a pure copper gasket. If you look on the right at our typical fillers, you're going to have something that's a silver plated copper or a nickel plated graphite. So it's really important to pay attention to the metals with the fillers and try to minimize the galvanic corrosion, galvanic differences, and bring those closer together. So this is a typical chart. This is a chart that's found in our catalog. These are typical housing design materials. So, first one on the chart, 6061 T6 converted coating, class 3 finish, are nickel plated aluminum particles, passivated silver plated aluminum, which has been a gold standard of corrosion for years. Those are all excellent choices. When you move down the chart, as you saw in the previous chart, magnesium is a very active material. It's very difficult to gasket a magnesium housing. I know it's very attractive to a lot of engineers because of its low density, but it's just not recommended in conjunction with EMI gasketing.
And really what we've done with this table is we've taken that galvanic series and done a lot of the testing at 168 and 504 hours salt fog exposure of our gaskets as well as the enclosure materials. So we've really put together a determination of what the best mating materials are in terms of minimizing that corrosion and increasing the life cycle of a lot of these applications. So here we see just a couple examples of some of our conductive fillers. And really, like I said before, they're the driving force behind the corrosion resistance. Each filler is going to have a different shape, a different morphology, a different density, and they're all going to have unique applications in terms of EMI shielding, conductivity, as well as corrosion resistance. And that's where we look at deciding which is the best one on an application by application basis.
So this is a typical shielding curve run on a pretty standard mil spec test, a solid D extrusion tested for EMI shielding. And you notice the top curve is the nickel aluminum by itself, not run through any kind of testing. And then we take it and we run it through a 2000 hour, 125C dry heat. We do 1000 hours at 85, humidity and temperature, and also the 500 hours salt fog. So you can see the curve, actually, the shielding decays and lessens over time. So corrosion really affects your ability in the field to resist susceptibility and also not radiate its own EMI interfering with other electronics around. So it's very important to realize that, yes, you designed it perfectly, but over time, you will see some shielding decay.
And here's just another example of the similar particle technology in nickel-plated aluminum, but incorporated into a robotically dispensed form and blaze gasket. So again, we see the same principles that shielding decay over the course of various environmental tests. And it's important to note that this isn't a material this isn't a property that's unique to this material. It's something that all EMI gaskets are going to go through as they're exposed and used in the field over the course of time.